Now it works. There we go. Yeah, you scared it coming up here, so. Hi, everybody. My name's Danny. I've met a lot of you by now. New research scientist at Geological Survey of Canada, part of the critical minerals group, where we're, like Mike said, trying to use a lot of new, novel, data-driven techniques to help speed up the value chain in Canada. Today we'll be talking about some of the work I'm doing trying to map outcrop descriptions, and I'm working with Chris Lawley at the GSC in Ottawa, and Charlie's been helping out on this because it's my first foray into deep learning, so Charlie's been very patient. I'm traditionally more like a field geologist. I love going out, measuring sections and gathering rock samples, looking at how veins twist and brecciate stuff and do geochronology and that kind of stuff. So I feel very kind of in place, but yet out of place when people are talking about all sorts of these very fancy models. So I would love to chat with everyone about kind of where you think this could go. Geologic data is largely gathered through points when we're out in the field. We can see in this upper map some great field traverses that people had in remote parts of Canada, fighting off black bears and mosquitoes, gathering information about the lithology, deformation, and all that kind of stuff. But when we go back and we go to make maps of this, we assemble all our point data, all of our structural information, geophysics, like the kind of second derivative mag, and we turn those into polygons. And this removes some of the nuance from what we saw in the field, stuff like key accessory minerals, alteration suites, deformation. And that's all fine and well, but we often use these polygons then for prospectivity modeling, stakeholder stuff, where we might actually really want to be able to go back to that original point data. And so it'd be really nice to be able to try to retain as much of this original point data as possible. Additionally, like Charlie was saying, we kind of enforce all these rock categories onto geochemistry, which is very continuous. And so, again, it'd be nice to kind of retain as much of this original information as possible. So the goal of this research is to overall create geologic maps of kind of numeric text embeddings that would be representative of their original outcrop description. So this would be lithology, plus or minus alteration, plus or minus this mineral or that mineral. And then we'll kind of take our embeddings, put it through some kind of wacky architecture like you can see there, and then end up with a map. Maybe we can create map boundaries, maybe we can query this for critical minerals. For those who are not kind of used to natural language models, they're trained in a way to more or less associate words that are more often co-occurring in a sentence or document. That's kind of what Paul was talking about and did a great overview of kind of how we can use these to query documents. Once we have a trained natural language model, we can take words, put them into the model, and get some kind of numeric representation out. And if the words are more closely associated to each other, they'll kind of in numeric word space kind of plot close together. So cat and kitten, very similar. Cat, dog, kitten, more similar to homes or houses. There's all sorts of really fun kind of demonstrations of this where words with similar relations often are distanced similarly. So king and queen kind of have a similar distance to man and woman. And those of us who kind of use these models have seen a lot of this kind of stuff. If we want to get the kind of semantic gist of a set of words, we can average all those vectors together, and we get, in this case, sandstone, gabbro, pyrite. We can average to some kind of outcrop description where we have all those kind of geologic entities put together. For this work, I'm using Chris Lawley's GLOVE natural language model. So in his recent publication, I showed kind of released a GLOVE and a BERT model and documented kind of how, when you train these models on a lot of geologic text, how we retain a lot of the geologic knowledge that we would associate, where we now have a bunch of kind of sulfide minerals that we find in hard rock reports all clustered together. We can have iron-loving minerals kind of all clustered together in that sort of. For the actual outcrop descriptions, I'm using a database in Quebec, so the eastern part of Canada, where there's about 400,000 outcrop descriptions that are all rigorously input into a database. And this goes back about 100 years worth of outcrop geology that folks there have kind of compiled. And so there's three different parts of the database. There's the outcrop information, the lithology information, and the structure information. So at each point, this stuff would be input. So outcrop information is like the size, the location, a very unstructured description of the outcrop. So whatever the geologist wanted to wax poetically about, this tortured, deformed, or beautiful, or all these things that, we'll see if that works. These kind of really unstructured descriptions, but then we also have the lithology, which would be more of a pick list. So there's a great kind of foundational data set where we can look at just lithology. So in this case, we have two schists. So they would kind of plot the same, but this one schist is chlorite hornblende plagioclase, fine-grained. Then the other schist has chlorite, epidote, garnet, sulfides, hornblende plateau. So we might be able to retain maybe the sulfides information if we're after a certain type of sulfide orbitals. And then we also kind of structural information about lineations and planar features. So the first thing I did was I took all the database lists and see if they existed in Chris's glove model. And so we can see some TC embeddings of different minerals, different lithologies and different minerals. They're in the database. So in the top left, we have lithology clusters where we see a bunch of like iron formations clustering together, different types of sedimentary rocks clustered together, and then these metamorphic rocks in the top left. Minerals, again, kind of clustered together, kind of how you expect, sulfides, near sulfides, different salt solutions of feldspars and garnets and that sort of thing. They're all together. We're missing about 148, 10% of the database list. Not all of them occur in the study area, and some of them are very obscure minerals that I've never heard of, but that doesn't surprise me. And then, then I've been changing a lot of informal names. Some are just something bearing whatever, so those can be changed pretty easily. One thing that I'm playing around with is how we kind of weight these descriptions. So when we're taking our averages, we might want to weight our main lithology differently from its kind of accessory minerals, because that would kind of allow us to go from just 100% lithology, where we have individual lithologic groups, to these kind of lithologic clusters that are dispersed by their component mineralogy. So I don't know if that'll be important in the long run, but it's something I can do in the code. For the actual place where we're going to be doing this, working up in the Ngava Peninsula of Quebec, so the northernmost tip of Quebec, where we have the Churchill and Superior Cratons kind of coming together, these Archean Proterozoic rocks. We can see there's, in this image, all these different polygons of different tectonic domains of these greenstone belts and kind of other Archean platforms, and quite complex geology. So when we quickly plot up the geology here, and some of the outcrop points, we have granite diorites, some schist, basalts, and gabbros, and we don't really need to pay attention to the color of the individual dots. It's just that there are kind of changes in dot color associated with these map polygons. So the color of the dots is just red, green, blue, PCA transformation of the word embeddings, and we can see that overall that the map follows the underlying kind of observations, which is nice to see. And then lastly, we're working up in Ngava because there is a great geophysical program up there in 2014 that had a bunch of kind of magnetic and radiometric surveys flown, as well as much more detailed geology than what I'm displaying here as well. So to prepare this data, I took the natural language embeddings, put them through PCA with whitening, and that kind of, the first three principal components account for 80% of the variance of all the natural language, of all the kind of outcrop descriptions in the area. And then whitening kind of just like we would all kind of standardize data going in, just kind of recenters and scales the data. So when we give it to a deep learning network, it balances the loss function and where the neural network is kind of spending its attention. And then using a linear transform like PCA kind of retains a lot of that initial embedding structure. So I'm using Charlie's 2023 kind of architecture, where we're going to be feeding it raster snips down kind of a convolutional chain, and then the location information along geophysics down another arm of the neural network, and then co-predicting principal components 1, 2, 3 from there. So some really quick results. So these are three in the columns are PC 1, 2, 3. Top row is a kind of our known embedding, and then their bottom rows would be our predicted embedding. And you can see that overall we're getting a lot of the same trends, which is great. So we're being able to map the overall the general geology, but we're missing some of the really high highs. So some of the really bright yellows we're missing in PC1, and then some of the really sporadic kind of high values in PC2. And so overall the model's too generalized, which I think is a nice problem to have rather than being able to have to underfit things. And then when we go to look at this in like a red, green, blue space, so combining all those into one image, more of kind of, I guess, a map view. We have our kind of predicted values up here and our raw values down here. And so looking at the, again, we're kind of missing some of the really high highs, some of these really bright teal blues. And then looking in numeric word space, we're getting overall the right kind of structure for the data, which is, again, great to see. And then in this right column is just the testing and validation data. So ultimately, we're going to try to produce like full maps of this, and I think that's going to be really helpful for trying to do prospectivity in two ways. So because we are kind of predicting these PCA embeddings, it's retaining that underlying natural language structure. And then we can kind of provide it any outcrop description that we're interested in finding. So we can come up with some kind of pegmatite with spodumene, and then we can use any sort of distance metric to find that sort of outcrop. And so here we're just looking at pegmatite embedding, a gabbro embedding, and basalt embedding. And then we could use any sort of distance cutoff. Because it's, again, word associations, we're also finding similar type rocks. As a function of distance. And it's very interesting that even though we have like gabbro and basalt, both mafic rocks, one extrusive, one intrusive, you're not necessarily like highlighting up the kind of mapped areas that you would expect for neighboring kind of mafic rocks. So that was surprising to me. And then once we have kind of fully predicted maps, we can use these as like kind of a continuous geology layer in any kind of supervised learning that would be interesting to try. So future work of this project, this is something I'm kind of doing off the side of my desk, is making full predictions using AWS because my laptop can't handle it, and then looking at kind of how we might be able to draw map boundaries, and moving towards kind of remaking that geologic map, seeing how it matches or how it might be different, and maybe incorporating structural information for trend prediction, because we have that at a lot of the points where people have gone out and measured strike and dip. Then there's a whole lot of other applications that might be interesting to look at where we want to do spatial interpretation, but there are nuanced descriptions that come with it, or they matter, and so that'd be like metamorphic grade or crustal level, where we can kind of use the same database to map different phenomena. I realize that I don't have a conclusion slide. So in conclusion, I think that Charlie's right that we need to start mapping kind of fundamental rock properties in a continuous way, because I think we lose a lot of information when we go to polygons, and we use polygons for so much in this kind of field. And this is very much kind of like proof of concept at the moment. When I submitted my abstract, I thought that I was going to be doing a poster. But I hope you all enjoyed, and I'd love to chat with anyone about it, so thank you so much.
Danny. Any questions?
I've got a quick one. Is it time to shred the geological textbooks that have sharp boundaries based on mineral composition and geochemistry and come up with something that reflects reality better?
I don't know if I'm the person to answer that. But yeah, I think that, I think everyone that's been out in the field has realized that there's a lot of question marks when we give these things. When you're looking at something, especially when it's covered in lichen or a terrible exposure that's like, I think it's this, or something that's been horrifically altered. But, I mean, fundamentally, humans put things in categories, so we'll always stay there, but I think that it's just part of learning geology that when you see something on a map that you're not going to find just that in that box.
Okay. It was kind of almost the same question, a little bit different. But when the people are listing things like feldspar, obviously there's varieties of feldspar and things like that. How do you deal with that? Do you have kind of anything built into the system that kind of allows you to have a confidence of its identification, or if you can break it apart into subsets and things like that? Or?
Yeah, so people will. There's definitely examples where there's feldspar one outcrop and other kind of more specific things elsewhere, especially if someone's like done petrology and there's samples associated with it. But ultimately, no. But in word space, they'll be really closely associated. So maybe if you are looking for a specific outcrop and you're after just a certain type of feldspar, whatever plagioclase, it'd be like you might highlight other things, but those are going to be like the closest outcrops associated, I guess.
Okay. Yeah, so the proximities,
Yeah.
Okay.
I think we can squeeze in one more.
Yeah. It's not exactly a question, it's more a remark or what I'm thinking. 20 years ago, Julian Ortiz and I were discussing with André Jourdain about geostatistics, and at the Geostats Congress in Canada in 2004, I remember there were a couple of nice talks about characterizing the entropy of forecasting for various geostatistical techniques. And I'm wondering whether the work that has been done there to see whether, okay, I'm talking about this continuous versus discrete debate. I mean, should we interpolate discrete categories and then do the continuous modeling, or should we do everything continuous and then try to reconstruct the sharp boundaries from there? And in terms of prediction, this has been studied quite a bit in the geostatistical community, and one argument that Journal had at the time was that all the Gaussian or multi-Gaussian assumptions tend to have maximum entropy in terms of prediction away from the data. I'm not quite sure whether this is also the case by more sophisticated AI techniques, but that would seem, having a look at these fundamental disorder measures for spatial forecasting could be a possible way to try to decide or help decide what's the best way forward.
Yeah, I think it's challenging because if you went from like the continuous thing that you would map in the field would be geochemistry, and that's very costly to do and very slow because you're going to be grabbing samples and writing down what they are anyway. So it's you can't sample every outcrop, but you can definitely walk between them and make huge inferences or map contacts and that kind of stuff. So, yeah, don't really have an answer for the first part, but yeah, the second part is very interesting.
Okay, let's thank Daniel again.